Hello and welcome back. In section 13.3, we get to work with Hamilton paths and Hamilton circuits. So the idea in this section, we've already looked at the famous Keinsberg bridge problem. This one is going to relate to what's referred to as the traveling salesman problem. So the idea is you want to find the least expensive way to visit every vertex. So let's say we have 4 cities. We'll call them Alpha, Bravo, Charlie, and Delta. And the idea is that now our edges are weighted. So the cost to get from A to A is nothing since you're right there. Similarly for getting from B to B, or C to C, or D to D. Going from A to B cost 70. A to C will cost 90. E to D will cost 100. And that makes this guy 70 as well. So some graphs will have different costs based on the direction. So from A to B, what might be one cost, and from B to A might be a different cost. On this one, we're going to keep it a mirror image. We'll keep it the same. So 110 between cities B and C, 60 between B and D, and 120 between C and D. And then, of course, our mirror images here. So A to C is still 90. A to D is still 100. B to C is still 110. B to D is still 60. And C to D, $1.20. So we'll assume that these are in dollars. So we can arrange these to make a graph. So you're already familiar with having vertices A, B, C, and D. And I'll show you 2 kind of common ways to represent this graph on 4 vertices. And this will be a complete graph on all 4 vertices. So in other words, every vertex is connected with an edge to every other vertex. This is one option, option for the graph. However, as you can see, we have then edges crossing. If you like the planar embedding that we talked about before, we can arrange these in sort of a triangle with one city in the middle. And these aren't necessarily going to be drawn to scale. I'll just arbitrarily label them. So then we go back to our table and we make a weighted graph. So a weighted graph gives a cost to an edge. Now that cost might be the time, it might be dollars, it might be distance, but it has some unit of measure associated with it instead of every edge being counted the same. So let's see, C to A to C to B was a cost of 70, A to D was 100, A to C was 90, B to D was 60, C to D was 120, and B to C was 110. So some similarities and differences between Euler paths and Hamilton paths. So recall, in an Euler path, we want to use each edge Hamilton path we want to use each vertex. We don't care if we use all of the edges to do that. In fact, typically we wouldn't. And each of these is, of course, exactly once. So some examples of a Hamilton path. From A to B, from B to C, from C to D. That is a Hamilton path. If we return back to A, we can make a Hamilton circuit. So path and circuit are defined as they were before. A path is just traveling along edges between vertices. A circuit returns you to the original. So an example of a Hamilton circuit may be D to C to B to A and back to D. Those certainly aren't the only Hamilton paths or circuits, they're just some examples of them. And we'll come back to the cost problem in a bit. But first I also want to cover the idea of a complete graph. I mentioned it but didn't formally write it up. So a complete graph has an edge between every pair of vertices. So we'll start with, and let's just do a little one of 3. 3 vertices, 3 edges. Two vertices would trivially just have one edge. Complete graph on 4 vertices. See if you can draw on every edge and count them up. Go ahead and pause it and see if you get the correct number of edges. Okay, welcome back. So 4 vertices. Hopefully you found 6 edges. 1, 2, 3, 4, 5, and 6 on the diagonals. Okay, see if you can repeat that with 5 and 6 vertices. See if you can complete each of those 2 graphs. Okay, welcome back. So on 5, I'll just skate around the outside first. 1, 2, 3, 4, 5, 6, 7, 8, 9, and lucky number 10 there. I don't have anything else I can connect. 6 vertices. Again, I can just skate around the outside first. 2, 3, 4, 5, and 6. 7, 8, 9, 10, 11, 12, 13, 14, and 15. And we'll take a look in a moment on where we get that formula. The reason we cover the idea of a complete graph in a little bit more detail, every complete graph has a Hamilton circuit. So if it's a complete graph, you're guaranteed it's there. It's not guaranteeing you'll find the best one easily. It's just saying that it does exist. There has to be a Hamilton circuit on there if it's a complete graph. Alright, so how many are there? So let's start with our smallest complete graph that are, well, other than the trivial one that has just the basic point A to point B, something with that. We'll start with at least 3 vertices. We're looking to see unique Hamilton circuits, so we'll want to label these out. So complete one could be A to B to C to A, or A to C to B to A. We could start at B, go to A, go to C, go back to B. Start at B, go to C, go to A, go back to B. And of course we can start and end on C. C to A to B to C, C to B to A to C. Now really though, we can really break that down into basically two categories. So we'll call this number 1. So A takes you to city B, takes you to city C. We also see that happening here. A takes you to B, takes you to C, takes you to A. A takes you to B, takes you to C. So those three are considered kind of equivalent. They just have different starting cities. The other one, we go from A to C and back to B. We'll call that category 2, A to C to B, category 2, A to C to B, category 2. So they're two unique. Hamilton circuits. So since these are sort of not unique, starting at a different city but just following the path, when you're looking for how many unique Hamilton circuits there are, pick one starting place and just look at all the permutations from there. Okay, so this is one version of the complete graph on 4 vertices. You've also seen the square with the 2 diagonals in it. So see how many paths you can take that start with A, or I'm sorry, circuits. Hamilton circuits that start with A. So go ahead and pause it, see how many you create. Welcome back. So you can do A to B, B to C, C to D, back to A. And then I would just kind of go at this systematically. So I'll just change the last 2 cities. So A to B, go to D, then to C, and from C back to A. And then I'll say, okay, I've exhausted those. Let's go A to C. Then I can go to city B, city D, back to city A. And I know that all these edges exist because this is a complete graph. Every edge that's possible exists on a complete graph. We can go A to C to D to B to A. And we've exhausted all the ones that start with A and go to city C. So then we'll start at city A, go to city D. So A to D to B to C to A to D to C to B to A. So there are 6 unique Hamilton circuits. So one tool we're going to need on these sort of how many ways can these things happen is the factorial. We'll get to play with the factorial lots more when we go over our section on probability. But for now, just a basic intro to factorials. let n be, and we'll say a whole number. Some books phrase that as non-negative integer. Two different ways to say the same thing. So we're not talking numbers like 3/4 or -8 or 15.2 or 1/9/16, 0, 1, 2, 3, 4, 5, 6, etc. N factorial is minus n times n minus 1 times n minus 2 all the way down to stop when you hit the 1. So for example, 4 factorial is 4 times 3 times 2 times 1, or 24. Let's see. 6 factorial, 6 by 5 by 4 by 3 by 2 by 1. Well, that's then 24 by 30, so that is 720. So as you can see, they get quite a bit bigger very quickly. One other definition that we need here, define 0 factorial as 1. So that 0 doesn't really fit the definition that all the other numbers would, but 0 factorial does come up quite a bit, and all of the formulas will work smoothly if we just use this definition that we've decided collectively in the math community that when we see 0 factorial, that it's worth exactly 1, and it doesn't work the same way of multiply until you get down to 1 that the other numbers do. So where this comes in is on how many unique Hamilton circuits there exist on n vertices. There are n minus 1 in parentheses factorial unique Hamilton circuits on n vertices. So I provided again, of course, you have a complete graph. So this does fit with what we saw before. On the 3 vertices, 3 minus 1 factorial, 2 factorial is 2 times 1, which is 2. 4 vertices, 4 minus 1 factorial is 3 factorial. 3 by 2 by 1 is 6. So no problem there, but let's look at what if we had, say, 11 vertices. So 11 minus 1, close it up, factorial, turns into 10 factorial. 10 by 9 by 8 by 7 by 6 by 5 by 4 by 3 by 2 by 1. 3,628,800 unique Hamilton circuits. So you can see where the traveling salesman problem would get a little bit difficult if we had to test out all of the 3,628,800 unique possibilities on just 11 cities or 11 vertices. So we have basically 2 options. So option 1 is what we refer to as brute force. So in this method, our algorithm, remember an algorithm is just a set of directions. Draw a complete graph with weighted edges. All possible unique Hamilton circuits. Find cost of each. And just pick the Hamilton circuit with the lowest cost. Distance, cost, whatever it is we're measuring, time. So this takes us back to that traveling problem that we looked at before. So let me flip back and we'll get our graph back now that we have what it takes to go through this. So we have A, B, I put C down here, yep. Charlie and Delta in the middle. So this is the weighted graph that you have before in your notes. Go ahead and flip back and bring that back to your notes, and I'll go ahead and fill in. So 70, 100, 90, 60, 120, 110. So this is our complete graph on 4 vertices. So brute force says, okay, draw the weighted graph, done. Then we look at all the different arrangements that we can possibly have. Again, remember, make sure they're unique. Again, arbitrarily, we'll just start with city A, whatever one that is. So we'll go A to B to C to D back to A. I'm going to skip spaces in between just so we can insert values on our next step. A to B to D to C to A to C to B to D to A to C to D to B to A, and A to D to B to C to A, finally A to D to C to B to A. So a complete graph on 4. Remember, we have then 6 Hamilton circuits. So step 3 is assign the cost. So A to B was 70, B to C was 110, C to D was 120, and D to A was 100. A to B was 70, B to D was 60, D to C was 120, C to A was 90. A to C was 90, C to B was 110, B to D was 60, and D to A was 100. A to C is 90, C to D was 120, D over to B was 60, B back to A was 70, A to D was 100, D to B was 60, B to C was 110, C to A was 90. And our last one, A to D was 100, D to C was 120, C to B was 110, and B to A was 70. Okay, so I'm going to go ahead and pause the video for a second while I have TI go ahead and tally those costs for us, and I will find the cheapest route between these four cities. Okay, so through the magic of editing there, $400, $340, $360, $340, $360, and $400 respectively. So our cheapest journey is going to be, it looks like, $340. Not path, strictly speaking, it is a path, but also a special kind circuit. So either one of the two that were $340. So I'll just pick the first one, A to B to D to C to A. And it should make sort of intuitive sense on this, that we would have different costs for going different ways. Think of if you were traveling across the country and had to hit Los Angeles, Chicago, and New York. The shortest way would be to start either on the east or west coast and drive across the country. The more cumbersome way would be to go from Chicago to New York and then from New York to LA, because you're backtracking quite a bit. Same idea here with the weighted edges. There's going to be different circuits you take that are going to be more efficient. So on little problems like this, where we have 4 minus 1 factorial, 3 factorial, or 6 possibilities, no problem. Brute force, you can just run that right through. When that's not available, since we don't want to try that on, say, the 3,628,800 possible Hamilton circuits on 11 vertices, we would want another method as well. So option 2 is called the nearest neighbor method. So we're going to draw a complete weighted graph, just like the brute force method. Identify the starting vertex, so you're basically going to look at the weights and find the smallest one. Use the, sorry, got my stuff backwards there. Use the edge with the smallest weight. Reach a second vertex. Select an unused edge. Reach a third vertex. Also unused vertex. So you're going to repeat that until all vertices are used. Turn to first vertex, calculate cost. So this is not guaranteed to be the most efficient. All it's saying is that, yes, this is a good idea of what we think would be a nice path. It's not guaranteed it's the best way. So this is a good estimate, not a guarantee. And let's try this on a complete graph on, let's say, 5 vertices. Okay, so should have 10 of those. Let's see, 4, 5, 6, 7, 8, 9. And who don't I have? And across here, we'll call this guy. Let's see, we haven't used a 7. Okay. Alpha, Bravo, Charlie, Delta, Echo. All right, so we're going to use the nearest neighbor method. So we've drawn a complete weighted graph. Step 1 is already done. Identify the starting vertex, the vertex with the smallest weight. So the weight of everything coming out of vertex A uh, 2 and 6 and 8 and 4, so we have 10 and 10 is 20. Total weight of B, let's see, we have 4 and 8, 12, 22, plus 8 is 30. C, we have 8 and 8, 16, plus 11, 27, 27 and 9, 36. D, 9 and 10, 19, plus 5 and 6, 11, 19 and 11 is 30, and E, 16, plus 9, 25. Okay, so in this case, it happens to be that A is our minimum weight. Not always necessarily the case. Just happened to work out on this one that A was the minimum weight. So A is the vertex with the smallest weight. Among the 4 paths to choose from there, 2 is the least expensive, so we're going to go from A to E. So now I've used up, there's my starting point, there's our first stop. I can't go back to A, I have to visit one of our other 3 cities. My costs are 7, 11, or 5. I'll go with the 5. So that takes us to D for 5. Again, I can't return to A yet. I want to form a Hamilton, excuse me, a Hamilton circuit. So I have to visit either B or C. B would cost me 10, C would cost me 9. I'm going to go to C. From C, I have no choice but to go to B for 8, and then back to A for 4. So I don't know for sure that this is the cheapest path around it. It might be, but it might not be. Brute force, I know for sure that it is. Nearest neighbor, I think it could be. I don't know that for sure. So then let's see. So we have 7, 9, 16, 24, and 4, 28. And we'll assume those are dollars. If they were miles, I would put miles, whatever unit we were working with. Whatever the original unit is, make sure it's included in your final cost. So that is the best Hamilton circuit, at least estimated by our nearest neighbor method. So some problems to try out. On 13.3, I would try out 1 to 8 all, and 9 to 31 on the odds. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.